Hello everyone. In this video, we are going to discuss about a very common problem which is generally asked in the topic of trees. The question is, if you are given a tree, binary tree, you need to find the path of a node from the root node. Please note, you have to find the path. You don't have to find whether the node is present or not, but you have to find the path of a node from the root node. So for example, if this is our tree, binary tree, and our root node is 1 here, and if let us say you have to find the path of 5. So the path of 5 is 1 to 2 and 2 to 5. So this is our path. So our algorithm should print out 1, 2, and 5. It should not just print out 1 to 5, but it should also store the path in some persistent data structure so that we can use it for later purpose. Okay. So let us discuss about the thought process which comes in our mind as soon as we hear this question. So the first thing that comes in our mind is like, okay, we have to find path of, let us say, 5, and the correct solution to it is 1 to 5. Can we do it through traversal? That is the first approach that comes in our mind to any of the beginner candidate. So let us just discuss that also. Let us say we have the traversal algorithm with us, and the pre-order gives us 1, 2, 4, and so on. I have written all these things beforehand. So this is our pre-order, this is our in-order, this is our post-order, and what we need is 1 to 5. We can see here that 1, 2, and 5 is not in a sequence format, because none of the traversal algorithm, it gives exactly to any of the leaf node, the path to any of the leaf node in a right way. Okay, so in a way we can conclude that getting the path from a traversal algorithm is not a good idea. And also we can say that, because we don't know beforehand that, okay, 5 is in this subtree or this subtree. So we cannot make a decision that, okay, we want to go to this subtree, then we want to go to this subtree, and so on. We cannot make such decision beforehand. And that is why the traversal algorithm will not be a good fit in this situation. So the approach of traversal algorithm is not going to work for us. Let us step further that how we can solve it. So some of the things that can be clearly said here is that we have two premises here. Okay, the first one is that we need to store the path somewhere so that we can use it for some data purpose. We don't just need to print it. Okay, so either we can store it in array data structure or dynamic array. So just think in our mind, which data structure is better, array or dynamic array? In Java, we use list for the dynamic array, and similarly in C++, we use a vector for it. Both are conceptually same, where we can keep on adding one element at the end of the data structure. Okay, so yeah. So just imagine if we have a very large tree and it is having thousands of nodes. Is it a good idea to create an array with pre-populated some number of that size? No, right? Because we don't know beforehand that what is going to be the size of the input tree. So definitely array is not a right choice. Dynamic array is a good choice. Why? Because we can just keep on adding as and when required. And as soon as we are finding a new node, we keep on adding one more element to that data structure, let us say vector. So one thing is sure now that we want to store our output in vector or list, whatever. Second thing is also sure that there are only two types of traversal we can do, either recursive or iterative. In this situation where the subtree is again having the same sub problem for the bigger problem with just one small change that we have already traversed one level down. So we can very easily map this question into a recursive function or recursive mathematical operation, definitely recursive call is going to be our answer. We can implement the same solution or same recursive solution using iterative method also. But in that case, we will have to deal with the complex stack operations ourselves. Because in the recursion also, we like compiler is handling the call stack procedures for us. Like, it will keep on saving the function state of the previous call into the call stack, and then it will call the new function and so on. And when it recurs back, it starts popping one by one each of the call function calls. So compiler does the same task of the stack handling. And in case of iterative, if we want to take it in an iterative approach, we will have to do the same. So we will take the recursive approach. Now these two premises are made. Let us discuss more that what should be the return type of this function or this algorithm. So two things come in our mind, that either it can be a vector, because that first impression is that we want at the end the path of the node, okay, and it will be saved in a vector integer format. So definitely if you return the vector int, we will get what we need. Second approach is we can get it through the Boolean variable that, okay, a path is existing. Also, the thing to be noted here is that second thing we need about the function is parameter. What all parameters we want to send to each of the recursion call. Definitely a root pointer would be one parameter for sure. A value pointer, that the value which we are going to search and find its path from the root. The third variable also we need to send is the vector where we are storing the path, right? Now the question is, do we need to store the path in a normal vector integer variable, or do we need to store it in a pointer? Which one is better? Let us see that. Okay, I am discussing this in a thought process manner because it will help a beginner level candidate to understand that how this kind of algorithms are derived, okay, or how to think this kind of solutions without any help. So let us say that we are taking the case of we are returning vector int, okay, and we are taking the variable as root node and a pointer to a vector integer data structure, and obviously a value which we need to search and find its path. One point to note here is that if we will take a simple vector integer and not a pointer, what will happen? In each of the recursion call, please note here, a new vector variable will be created, because that is how the recursion works. That in each of the recursion call, when it is calling another recursion function, it saves some of its properties, like the list of parameters, the list of local variables, so local variable 1, local variable 2, and all, and the address of the function, because once it will return back, it should know that what was the address of the function call, right? And also it should know that, okay, what was the local variable, all the list of local variables and the list of parameters and so on. So once it pops this information and it is in the program status of the compiler, sorry, interpreter, or whatever it is running the program, it will have the state, the previous state. Okay, so if it is a simple variable vector int, what it will save? It will save it as a local variable. It means that it is saving it as a copy. So definitely you are not going to write the same value in the same the path of the node in the same variable. That is why we need to use a pointer, or let us say a static variable in the case of Java, a pointer in the case of C++, a static variable in the case of Java, because the pointer will point always to a same address, and we are going to add one node at a time, which are occurring in the path in the same variable, sorry, in the same pointer, vector pointer. Okay, so please note that that is the reason we are taking the pointer approach. Okay, because we don't want to create a new vector each time, and then we have a value, obviously. Let us assume, so we have concluded that, okay, we will take the vector pointer approach and not the simple vector approach. And now we are discussing whether our return type should be vector int or a boolean. So let us say that it should be a vector int, because that is what sounds common sense at the first impression. So let us say that if it is a vector int, so our function will look something like this, that, okay, if this is our 3, 4, 5, 6, and 7. So at the first instance, what will happen is we will check whether root is null. So no, it is not null in this situation. But if it is, let us say, null, let us say we are pointing it to the left child of the 4, which is null. So what will happen? It is null pointer, so we will just empty our vector and we will return it. Right? We are returning here vector int. But let us say if it is not null, let us say we are in this situation, we are passing the address of 1. So what will happen? We want to push or add this 1 to our vector. Okay, please note I am using arrow operator, which means that v is the pointer, which it actually is. Okay, and once I have pushed in my list, so let us say my vector is this. Okay, it can grow to any size. So the first push is 1. Okay, and now I will check that, okay, if my root left is not equal to null pointer, so my root left in this case is 2, which is not equal to null pointer. Okay, so what I need to do, I need to call the same recursive function for the left subtree, right? But please note here, what I will get in the return of this, a vector integer of vector. So do you think how can I, so let us say if it will return me, if I want to get the path of 5, so it will return me, let us say 2 and 5. What I will do with this 2 and 5? I will have to then add this 2 and 5 in this primary vector pointer, right? Which is not going to take place because it is the same vector I am handling with the vector pointer. So you can see that there is no way to find out that, okay, what is the subtree's subsolution, and in the same way whether this is a correct path or not for the 5, 2 and 5, whether it will also try to go to the 2 and 4 path. So in a way, I want to say that if you will look closely here, that I'm not sure that how I will return the output of this left subtree and how I'm going to use it to determine whether the 5 is occurring here or not. That is why one thing we can derive from here is returning a vector integer is not a good idea. And we should look for the other option, returning the Boolean variable like true or false. Simply return that, okay, 5 exists in the left subtree or not, 5 exists in the right subtree or not. If it exists in the left subtree, let's focus on the left subtree, and so on. So if we take the Boolean approach, so please focus now below part, okay? If we take the Boolean approach, what will happen is, let us say our function is node path, everything remains same, a root pointer, a pointer to the vector, and the value which we are searching. We are looking first whether our root pointer is null. If it is, we will return simply false, that there is no path available for this value. Okay, because we have not found till now any value data, and we have reached the null. There is no path, and we will just push. If let us say this is not true, so we will continue the flow, push the root data into the vector using the pointer. Okay, and now check whether the root data is equal to value. If it is, then simply return true, that okay, we have found the solution. Now go and check the integer vector at the pointer v, and there you would find the solution. So returning true tells that, okay, go to the vector v and check for the solution. Returning false means there is nothing available. Going to the v will give you a path to the leaf node. That's it. It will not give the path to a required node. It will just give the path to a root node where it has hit the leaf. Okay. And let us say if the root is not equal to value, then what we need to do? We need to take a decision whether we should go to the left subtree or the right subtree for finding that particular value. Okay. So because it is returning Boolean, so we can very easily write that, okay, if the node path for the left subtree and for the same value, integer vector pointer, and for the same value, if it is true, or if it is found in the right subtree in the same way, then return true. Okay, so in a way we are saying that if in any of the left subtree or right subtree we are finding, it is, please note, it is an OR operator, we are finding the value, then return true. Pushing of the path will be handled by this. Okay, if we don't find, then what will happen? If we don't find, let us say in left path or right path, then what will happen? In that case, we will just pop or remove the last element which we have entered here. Okay, and what will happen? We will return false. So a false will be returned to this one and other path will be taken. Let us say we have not found it in the right subtree, so this will return false, but it will be true, so this path will be taken. So in this way we will find the solution. Okay, and how we will call it from the main function? Obviously we will create a simple vector integer, like vector integer my path, and I will, sorry, let us make it v, and I will pass the address of this v here in the function call. Okay, sorry, I have already created the path, so everything will be returned here. Okay, and the path will be saved in this, and this is my vector v, which I will pass for the okay, I'm sorry, we don't need to pass it in this way. It will return a boolean, right? I will just my result will be stored in this v, and I need to just check that if this this boolean value is true or false. If it is true, then I will print iteratively the content of the vector v, which will contain the path. If it is false, I'll print not found. Okay, so this is how I will handle. By mistake, I have written as a return type as a path, and then I'm comparing the size of the path and blah blah, all those things. Please ignore it, my mistake. Okay, now can we use this particular solution? So in this case, what will happen? If I will ask that, okay, what is the path of 5? So it will give me 1 to 5. If I'll ask, okay, what is the path of 7? 1, 3, 7. If I'll ask what is the path of 3, it will give me 1 and 3. But if, let us say, I have to find the distance between 5 and 6, let us say here 5 and 6. So distance, what does distance means? It is the shortest distance between the two nodes. So this will be the path. This is the distance between 5 and 6. 5, 2, 1, 3, 6. So the distance will be 1, 2, 3, 4. 4 length we have to travel in order to reach from 5 to 6 or vice versa. Similarly, if let us say I have to find distance between 6 and 9. So this is the path. 6, 3, 7, 9. So the distance is 3 and so on. So is there a way I can find the distance between two nodes? So if you'll just close your eyes and pause this video for a moment and think about it, two things will pop in your head, two solutions. One is common ancestor method. It means somehow you will find that, okay, what is the common ancestor of 5 and 6? So 1. Now from 1, you find the distance of 5 and you find the distance of 6, you add it. That's it. done, right? Distance, you can find it using the same algorithm which we have just now discussed, the path of the of a node. So you will just find that, okay, how many like going down we are doing in that path, or how many elements are there in that path -1, that is the distance actually. So somehow we will find what is the common ancestor of these two nodes. Similarly, in the case of 6 and 9, the common ancestor is 3, right? So we are talking about the lowest common ancestor, because the common ancestor of 6 and 9 is 1 also, but we are interested in 3 because 3 is the lowest ancestor which is common to both and 6 and 9. So we are interested in 6 and 9. So for this situation, I will have to derive a way or a solution to find what is the common ancestor of 6 and 9. Okay. Other method is to find the distance between the two nodes using root node as a common ancestor always. So in that case, what will happen? Let us say I know that, okay, 5 and 6. So the path to 5 and 6 from the root is 1, 2, and 5, and 1, 3, and 6. Now, if I have to find the distance between 5 and 6, what I will do? I will see that, okay, 1 is the common in both because it is a root node, obviously. So I will have to travel 5, 2, 1, 3, and 6. Similarly, the path of 9 and 6 from 1 is 1, 3, 7, 9, and 1, 3, 6. So the common part is this much. So how I will travel? 9, 7, 3, 6. Right? So in this way, what will happen? If let us say we have two nodes, we will find the path of both the nodes from the root. We don't need to find common ancestor, right? We will just find the path from those two nodes with the root node, and we will compare how much part is common to them. Okay, and after that, how many elements are there? So the common part is 1, 3. After that, there are 2 elements, and here there are 1 element. So I will consider the leftover element, add the leftover elements number plus 1. Okay, so 7 to 9, 9 to 7, 7 to 3, and 3 to 6. Okay, I'm sorry, I don't need to plus 1, just the number of elements. Like it's a common sense, you will just find out how to derive it. The main idea is to use the idea of finding the distance between two nodes as a for finding the distance between two nodes, you need to reuse the idea of finding the path or the distance between a node and the root, and then using it. That's it. So just for understanding, like we are visiting, in the case of finding the root node to any of the nodes path, we are visiting all the nodes only once. So that is why the time complexity of the solution is big O of n, even though it is a recursion, but we are visiting each of the node once, so it is O of n. In the similar way, if n is the number of the nodes in a tree, finding the distance between two of the node is again big O of n for finding the distance between the first node and the root, big O of n for finding the distance between second node and the root, and for in the worst case, let us say the path is in the order of n. So traversing both path and finding the common path and so on, and finding the number of distance, number of traversal, number of steps we need to travel in order to reach from one node to another, removing the common part, is O of n. So asymptotically it will be O of n. Right? So this is the solution. Thank you for watching this video, and if you like this video, then please subscribe to this channel to see some more such videos, and like this video. Thank you once again.